All right. Which one I'm showing here? Let me see. Okay. Yeah, looks like I'm sharing the right one. Can folks see the PowerPoint?
Yes.
Okay. Let me switch to presenter view, so it's bigger. Okay. Let's get started. Okay. Yeah. So this is actually this PDI talks for the representation for machine learning. I mean, the representation itself it's basically for the purpose of having a sample project to show folks that how we do machine learning in this organization. To my knowledge, a lot of you guys already went through the Coursera class, right, on the machine learning, and many of you actually went through the next series of the class on Coursera, which is pretty good, very good as well, the specialization series. So I know some of you guys, quite a few of you guys are very good into this already. But this title is the representation is really it's mostly for the purpose of people who are who just started machine learning, and for folks that already do this for a long time. This is probably too basic. But still, we like to use this tech talk to show you some of the tech knowledge and tools we choose to do machine learning in this organization. So hopefully that is useful for you as well. So stay with us. So what we'll do today? So we're going to start. We're talking about what we're solving for. The project we picked as a representation is one of the project we did in the past, which sent out an email about a month ago. So it's about detecting the feedback and echo sound from the audio stream. So I will talk about the specific problem a bit later. Just on the agenda side, so after we do and then we'll do a quick demo after we walk through the detail of the project, and then we'll walk through the wiki page and code to hopefully give you an idea of how we actually do things at a very detailed level. And we'll save about hopefully we can save 10 minutes for a Q&A at the end. But even with that, I would encourage you guys to ask questions. So you don't throughout the presentation. You really don't have to wait until the end of the presentation to ask your questions. Okay, so what's the problem? So this is a problem everybody knows, right? So the audio feedback and echo sound is one of the common user pain in many meeting products, and unfortunately, GoToMeeting included. So this is the issue that you see when you have a lot of more than one participant or GoToMeeting attendees in the same conference when they sit next to each other. When you have a multiple mic and a speaker turned on, in a nearby location, then they tend to have these issues. And similarly, we have audio echo issues that generating in similar matters. So this is the really loud pitch that you guys hear, right, when you sit next to each other, and it's very annoying. And unfortunately, how do we do this? How do we solve this problem today? Well, unfortunately, there's really no solution to my knowledge at this point. And it is a problem not only for GoToMeeting, for our competitor product. I test many products, and I see this problem in pretty much every meeting product. And the solution we have today is pretty much just managing it, right? We can't really solve it, so we tell people around, to mute your mic, to turn off your speakers, and for people who are new to the product, not experienced using the product, a lot of times they just have to give up. So we decided to give a shot with machine learning. One thing I want to spend a minute here is that what makes our thinking this way, right? Why do we even bother, or why do we think this is a right candidate or okay problem for machine learning? So we have some thinking process I like to share with folks. So the reason we think about machine learning is that we see this is a problem that is kind of complex to solve, using conventional software engineering, right? Like digital signal processing, the algorithm on that. There's a lot of corner cases and edge cases that may require you to do very complex programming if you want to do the conventional way. Well, I don't know. I'm not really into digital signal processing, so I can't really speak too much about that. But the way I see that is that the fact we don't really have a solution yet is probably due to it's just too complex to deal with all these different corner cases with conventional approach. But on the other hand, this is actually a really easy problem from human point of view, right? Like when this happens, when you see this loud pitch happening, for human ears, this is a really easy problem to detect. You can always tell there's a presence of feedback or echo, right, in the audio stream. It doesn't really, there's no ambiguity at all. And this triggers us to think that for a problem that is a bit hard to solve with conventional coding process, but really easy for human intelligence, you can see it clearly, you can hear it clearly, then we tend to think that this can be a decent candidate for machine learning. I'm not saying it is definitely one yet, because this subject to other conditions, such as do we have a decent way to generate enough solid training data to create a model to train it, right? So that's actually a condition as well. But nonetheless, just for the sake from the observation that it's pretty easy for human ear to detect the presence of that, make me thinking that this is a decent candidate for machine learning. So just want to share that thought while we actually take this direction to take a crack at this problem. Let me take a pause here so folks can hear me just fine. Is it all good so far?
Yep.
Mm-hmm. All right, good. Let's continue. So if you have any question, as I said earlier, right, just feel free to chime in. So with that thinking, we started taking, just like any machine learning project, we started collecting data. And so this slide just to show you the a typical machine learning project pipeline. So you started with collecting data, and then from the data you get, many times the data you got is just raw data and may not be correlated to your target state at all. In our case, the target state is actually try to predict the audio have feedback or have echo, right? For that, or it's a normal sound. So a lot of times the raw data is not predictive of that, so you have to do some creative feature engineering to generate a transformation of the raw data to find a way to make data to be predictive of your target state, your prediction. So that's actually one of the most critical aspects of any machine learning project. And for this talk, I will probably spend quite a chunk of time to explain how we come to feature engineering and what is the process we follow to come down to a very accurate, very effective set of features that are predictive of our target state. So with that, and then of course,
so actually, I do want to ask a question, right? I was going to ask if how they were labeled, and I think that's what you're showing in the next one, is that they were labeled using a signal intensity ratio.
Yeah, I'll come down to that. So
there's no person doing it. You were talking about human ears. I mean, but then if you were going to label it using that, then what's the machine learning? Then you just use that.
Yeah, the labeling process is actually for creating and training data. It's a process of having data ready, so you have something to train the model. And so once you got a model trained, the model is capable of predicting the.
Is the model what I don't understand is, if you have not a human label it, if you're trying to do it in an automated way where you're labeling it, then and that's your your final result that you're trying to get, then I don't understand how your machine learning, the best it'll do is to do this.
I don't think the labeling. I don't think the signal intensity ratio is going to say it has feedback in it. I think it characterizes the audio rather than labeling it as having feedback. Characterizes it some other way.
Right.
What does it characterize it as?
aren't you going to go over how you trained it, Peter, and
yeah.
in a later slide? So yeah, we should probably talk about how. Yeah. Get that.
So save that question a bit later.
It isn't about how to train it, right? I'm trying to understand what this point is. What are you labeling it as? If
the labeling is basically
output of the model is labeling basically.
Yeah, the labeling is the process about getting the. I'll come down. I'll tell you just in one next slide to say what is that data. The labeling is basically the process of characterizing your individual training example to be a normal sound or feedback sound or audio sound.
And that was my point.
And you have to put the human knowledge in there to tell the machine that this kind of pattern with a loud pitch is feedback, and that is just a normal sound. You have to give a sufficient number of training examples with this fact first, so that machine can learn from that fact to predict the future. Okay, so that process is always a man in the loop process. It's always a labeling. With the machine learning term, we call it labeling, right? There's some lucky. In general, it's always a man in the loop. You always have a human involved to actually tell you the fact. It's like you're trying to label.
I agree. If there is a human involved, then I would agree. It sounded like there wasn't a human.
There will be. I'll tell you a bit later. Just save that out. Yeah. So I'll tell you how we collect data with the painstaking and manual process. On the next slide. So let's just save that out for 1 second.
Also, I wanted to know how long the audio clips were.
Yeah, it's a very good question. So actually, let's jump there because this slide is pretty much done. So let's jump to the data part of collecting data since the question is being raised, and this is just about the slide I'm coming to anyway. So how do we collect data, right? So first of all, I want to mention that the audio clips that we are trying to collect as a training example, we decided to use a 1 second long audio clips. So you may ask, what was the big deal about 1 second? Why not 2 seconds or 3 seconds, right? Well, for training example, you need to fix the size of data as your individual training example, and we come down to 1 second. We initially tested with 3 seconds actually, but then the data is the feature is too big, and we tell ourselves that it's actually not necessary, right? Why is that? Because the reason we pick 1 second is that, again, based on the what a human is learning, right? As a human, how we learn, how do we know the audio have a feedback? By listening to the sound for just 1 second, in general, it is sufficient long enough time for a human to make a decision just in 1 second to know whether there are feedback in the audio stream or not. It's probably take less than time than that, right? But we just take a shot at 1 second. Even half second may be good. But you have to pick somewhere. So we started with 3 seconds. We found it's too long, and we can't really even have enough training example anymore with 3 seconds. So we choose to use 1 second, automatically increase our training example by 3 times, right? Which is pretty cool. Mm-hmm. But the bottom line is that the message I want to let folks know about is that the decision point on the 1 second or half a second or whatever is basically determined by what I consider a human can detect that. Right, that's your basis. If you actually make it too short that even human ear cannot reliably detect the presence of the feedback, then that might not be good enough, right? So that's the thinking process.
Yeah, I think and Malika, I think let's save the Q&A for end of the session because we need to go through the flow, and I think this is like disturbing the flow. So let's save the questions for the end and finish the tech talk. Let's do that.
I'm a little. I thought this was an interactive session. Peter
No. This is a tech talk. You can, yeah, but I'm saying save the questions till end. Okay.
Yeah, that's what I'm saying. Well, I guess if you don't want it to be an interactive session, that's fine. Then
Yeah. Okay. Thank you.
I can always look at recording. I think people who don't want an interactive session should.
You can
ask hold on. Yeah, hold on, guys. That's okay, right? So. We probably, for some question, we may not be able to answer to the ultimate details, we have to move on. I don't want to encourage, that's okay, right? So I don't want to encourage folks to have questions, but let's don't hang on for too long on individual one. It's good to have an interactive session, and some of the questions help to make the tech talk actually a lot more interactive, and we can do a deeper dive. So I don't mind that. It's okay, as long as it's not going too far into trenches. So yeah, again, right, on the labeling part you're asking. So once we identify the appropriate size of the audio clip, like 1 second, we collect about, in the end, 45,000 of them. And how do we do that? It's not automatic, right? We actually went through a very painstaking process to listen to the audio, especially for collecting the training examples that are labeled as feedback. For the normal sound, it's easy. We just got tons of webinar recording, YouTube recording. We got a combination of that, and then we just do using a tool to do an automatic cut into 1 second. Then done, right? We got about 30,000 of a 1 second clip. That's normal sound. It doesn't take any effort. It's very easy. It takes a lot of effort for us to generate about 15,000 or so audio clips, the 1 second clip that have feedback and echo sound. And we started with the painstakingly, just to manually listen to the audio. We created the scenario with all these speakers together to generate the feedback and echo, right? So we did that with a manual setup, and then we record our thing with different variations for about 1 hour, 2 hours. So you can imagine this whole 1 hour, 2 hour session are fully occupied with feedback and echo. And from there, we manually try to remove some of the silent period, some period that are actually not obvious, things like to make sure the data quality is high enough. I mean, after all, you need to make sure the machine can learn, right, very well. So that is actually the painstaking process. We listen to this 1 or 2 hours of this manual recording that is full of feedback and echo, and do the 1 second cut, and throw away those 1 second cut that's actually not so obvious, and keep those ones we consider a good quality feedback and echo sound. And boom, we got our training data. We're actually not able to get 15,000 of them, right? Which is the next one I want to talk about, which is we got about actually, where's that page? It's oh, it is here. Sorry, I missed that. So we actually only got about about a 1 hour or so worth of the feedback sound and echo sound, which is given the training we have, we consider it's not enough. So we use a technique called a data augmentation technique to increase our training set. Basically, we're using some tools such as Audacity, some other tool that we have great QA guys in our team. He used all kind of fancy tools to try to create based on the initial feedback sound and the audio sound we have, we create a variation of that. So basically, with data augmentation, we're able to increase our training set by almost 5-fold. So we end up getting almost 20,000 feedback and echo sound, and that's how we end up with in the end we got about 45,000 1 second audio clips as our training examples. So this is how we get it. Yeah. Question. Go ahead.
So the 3,000 1 second audio clips, were they generated by having a artificially long period of feedback? Is that how you generated feedback tone?
Yeah, we put a multiple speaker in the room, and we had people try to move around, right, to generate some variation of the strengths of the signals. Yeah, but basically that's how we do it. Yeah.
Did you verify that the distribution of this artificial sound is similar to the distribution of feedback in real life?
It's we did some verification, but pretty basic one. Basically, that's a very good question, by the way. So this reflects the challenge of any machine learning project, which is obtaining the data is one of the really challenging phase, right? You're getting data. So we realized the way we generate will not reflect all different settings, right? In real life, you're probably sitting in a big conference room or in a small room. You may have 2 people around you, or maybe 20 people around. So there will be different variations. But we did with our best effort, right? We try to get as much as possible, given the limited resource we have, to generate decent size of training data. In the future, of course, in order to get a really rich, a high quality training data, we may need to actually outsourcing this to, for example, Amazon Turf, all these other crowdsource company to actually generate data for us. But nonetheless, the limited effort we made so far got a decent training, and we use that to actually train some real life scenarios. it's surprisingly good. So that's what we have so far.
Do we have a confidence? Do we have a confidence level of how good the model is, given the data is somewhat artificially generated? Like, do you have some sort of number on how confident you are that how valuable it is?
Yeah. So definitely can come down to that. You know, we actually. So let me jump. Yeah. So we are down this slide. Let me just come to this one. So let's jump to conclusion first, right? Before we work the details. Let's just give you an end state. You know, you can look at. So with our, you know, with our training and with the model we established, eventually this is what we come down, which is we got about this is the performance. You know, we got out of all the data we have, we're able to detect correctly the normal sound, you know, about 99% of the time correct. And for feedback and echo sound, we got about 96% accuracy. So you can see that on the slide, you know, with about 1,200 feedback sound, we're able to identify it correctly about 1,100 times of time, right? And we misclassify our feedback sound as an echo about 34 of the time, and 5 misclassified as a normal. And so is similar for echo. So that's what we have.
So I think the issue in maybe the question was that, like, I assume that these accuracy numbers were computed on like a holdout set that was taken from the artificial data that you generated, but they don't necessarily reflect the confidence in real life data, right? And then that's not possible for you to estimate without collecting data from a different context.
Right. So again, that's a very good question, right? As in any machine learning project. So what do we do with this, right? So definitely what accuracy rate you get from your training set, especially some of your data is actually augmented, and also the data you generate is actually artificially generated. I mean, by artificial generated, really the generating process is a kind of a simulation of the real life scenario, right? You do have people sitting in a room and generate that. It's not really a software generated scenario. So it is actually real life reflection. The problem here is that it may not be enough, right? There's many different variations of a real life scenario that we may not capture. But nonetheless, what we do here is that, so once we got a model, we actually try to apply that to some kind of production setting, by having a real GoToMeeting to see, we actually did a hackathon time, we integrate with a GoToMeeting, and we do real people calling in to have feedback, just to see what is the prediction accuracy in production, right? In a real life scenario. It's still decent. I wouldn't think they actually can hit as near as a 99% kind of a case, but they're actually pretty decent, but again, in order to collect the performance of the production testing, you need to actually, again, went through labeling process and have a human man in the loop process to verify whether your result is accurate, is making the right prediction or not. And again, that's a long process by itself, right? Just like any other machine learning project. But nonetheless, that I do think that's a very good question, and we need more testing to know for sure how this would actually perform in production. Okay, but I don't hang on too much on that. We just take some time to walk through the representation, right? Whether I think the question is valid when we actually try to consider seriously to put this in production use, right? For example, for GoToMeeting, for Auto Engine. But let's save that thought for the future. And the purpose of this tech talk is really try to show folks how do we do machine learning, how do we follow, what kind of process we follow to get it working. So let's keep going. So audio data, right? Let me do a time check because we spent quite some time on the. Okay, we got 20 minutes. All right, so we have 30 minutes left. Let's try to be a bit quick on this. So just a bit of background for folks. Some of the folks in the audience probably are really audio expert, so this may be too much for you. But for folks who are actually not too familiar, just a quick intro on this, on the data. So the sample that audio clip is basically the 1 second long sound wave, right? It's continuous analog signals. And the way it is being represented digitally is that with a digital sampler, the sound wave will be sampled at a particular sample rate. And the result is a sequence of discrete time signals, or we use the term sample data to describe it. So for example, on the Mac, the original audio wave by default will be sampled with about 44 kilohertz rate, meaning that 1 second audio clip without any modification, you will have 44,000 data point for that 1 second audio clip. So this is a little bit too much, and we actually started testing with original, but then we found we really don't have that many training example, right? As I mentioned early on, we have 45,000. Actually, when we initially tried to do the validate our hypothesis, we only have half of that. So with 44,000, as a features, the implication is that you need a much larger than that number, right? The training example has been much more than that, and we don't have it. So how do we deal with this? So I'm thinking that okay, we can do sample reduction, right, for efficiency, and the command we use to do that is we use this open source tool FMPEG to with this command you can reduce the sample down to 8,000. So feature engineer, let's jump to that. And this one is I just spend a little bit more time on. So we conducted many quick evaluations using a tool called DataRobot, which I will give you a quick demo of how that works a bit later, with the following choice. So we tested with the original sample data, and then we found, we don't have enough data, so this is a pretty bad choice. And then we tested with the reduced sample data. We did a manual run of that. We tested with the audio feature, which we'll cover in detail what that means. We eventually come down to top 30 most impactful audio features, and again we do a further drill down. We end up using only one audio feature called OBSLR. So which one to use? This is actually the experience we want to share. Yeah, go ahead.
Is this the original actual audio samples, or are you transforming them into the frequency domain with an FFT?
We transform.
Okay.
We transform the audio into all this feature. Yeah. So, yeah, good question. I will cover a bit later on what kind of transformation we do for that. So to start with the sample data, right? So we tested with the original one, and we found we don't have enough data, and we tested with a really reduced sample data. We did many iterations with sample reduction to 2,000 level, to 4,000 sample rate, and 8,000 and 16,000. I want to mention this because I want to emphasize the point that we actually don't know, which one works better. But so instead, we're using this technique of, fast iteration to try to let the testing tell us what is a good outcome. So basically, this is the power of DataRobot. When we use that tools, we're able to do really quick iteration in parallel on many different variations, and have the testing result to tell us what is the right approach. So for example, I want to highlight a few points here is that, so when I test with, I initially go very aggressive, right? So I reduce the sample all the way to 2,000, and the prediction is to go nowhere. It's totally random, right? It's completely not working. And I tested with 4,000, I got some decent accuracy. I tested with 8,000, I found it's already pretty good. It's not as good as the auto feature, which I will cover later, but it's decent. And I changed to 16,000, and I found it's almost no different. So what this tells you is that, so when you do a sample reduction down to 8,000, that's probably a decent balance, right? You got a decent, you reduce your data size significantly. You're able to do this kind of testing with a small enough data training example set. You're able to get a decent accuracy without losing much to 16,000. So that seems to be a good outcome. And if you think about it from human ear point of view, I tested the sound, right, just with my own ears. I kind of realized why that is the case, because when I reduce the sample down to 8,000, as a human ear, I can still hear it pretty clear and loud. It's a feedback. But when I do 4,000, 2,000, I found even as a human, I lost track of that. I don't seem to be able to detect the presence of the feedback anymore. Sorry, there's some question from audience.
Yeah, so when you say that the error stays about the same when the sample rate is 8,000 versus when it's more than 8,000, like is it marginal error when it is more than 8,000?
No, I always do this double. So I do 2,000, 4,000, 8,000, 16,000. Is that what you're asking?
I know. Yeah. No, so you're saying that above 8,000, the sample rate, the accuracy is about the same.
It's just slightly better. It's not much, almost no difference. Yeah.
So if it's slightly better above 8,000, why wouldn't you use the higher sampling rate? Like you say that it's because of the fact that it's too high of a sampling rate, but then since the error actually supports that you get more accuracy with a higher sampling rate, why not use it?
Very good question. So let me give a quick answer on that.
Especially with feedback that ends up using higher frequencies.
Yeah. So I can give a shot at this, answer this question. So of course you want to get more accurate, right? And especially for the high pitch sound. But the reason we actually want to sacrifice that is because it's quite expensive to actually. I will come down to auto feature because later on we do auto feature instead of using sample to do it. It's a quite with a very fine grained sample rate. The training data is very big. The training process will be very slow and takes time, but that's okay, right? Training is who cares? I got a good model. Training I can afford to be slow on training, right? But more important is on the prediction side. In production, you have to feed this data to the prediction to the model to actually make the call, right? It's a feedback or it's echo normal, and that process will be also pretty expensive. So in the end, what you want to achieve is that if your accuracy is roughly the same, you actually also have to make the balance of okay, I want to make sure my model actually is very fast and practical, right? Not just theoretically very accurate, but useless in production because it would burn too much CPU. Right, and this will not be useful anymore. So I'm just trying to share the thinking. I'm not really saying using 16,000 is not good. I'm saying that for some practical thinking, and this kind of thing will probably apply to many other machine learning projects as well. That you have to make the balance of whether you need the ultimate 1% improvement for the accuracy, or whether you have to sacrifice a little bit to be practical, right?
Okay.
So that's the thinking.
Yeah. The other question I have is, so when you sample here, are you just uniformly sampling like the uniform frequencies? Like, so when you take downsample to 2,000 from 16,000, you're just like interpolating the 2,000 samples. Is that correct?
Actually, I don't know. For that, I can tell you is that I'm using this tool, right? The FIMPACT. It is doing whatever that. I guess in the world of digital signal processing, the right way to do the downsampling. I'm not doing something myself. Like I'm not picking every point out of A, right? That's not what I do. Yeah, I think there's some kind of a Fourier transformation, and they do some kind of magic, which I'm sure the digital signal processing expert in the audience will be able to answer much better than I can.
It's typically upsampled to the most common multiple, and then downsampled back to the what you'd need. Certain ones are easy, 16 to 8. You can do shortcuts, but in anything that's an odd multiples like this you typically upconvert it and then bring it back down.
Okay.
Yeah, what I was getting at is that certain frequencies probably predict feedback better than others. So like by uniformly sampling, you're wasting like dimensionality by like giving space to like frequencies that are less likely to predict feedback versus like you could have used those slots in the dimensionality to like pick a frequency that is more predictive.
Yeah, and along those lines, I'm wondering if the team has considered using a discrete wavelet transform instead of an FFT because it preserves both frequency and time information, and since echoes can be part of this, time information is actually kind of interesting as an input for the learning.
Yeah, it could be. So in the interest of time, that's a good discussion, right? I mean, actually, if we actually move this project for real use to be considered for the auto engine integration, I think that's kind of a discussion I like to get us to talk about. But in the interest of time, and remember the purpose of this tech talk is actually really for us to walk through the machine learning pipeline. But I appreciated the discussion, but I think we do have to move on. Okay, so okay, on the we talk about this slide. So then we continue our testing, right? We did we're testing with sample data. We got some result. We're not too happy about it. I think we got about 70-80% kind of accuracy when we do the 8,000 or 16,000 kind of sample rate. So to me that's a little bit still too random, right? So this some then just being not quite exposed to the signal processing. Nonetheless, I did quite some research on the audio processing, and I realized, okay, there's actually for many years that we have this wonderful work audio features that can be used to that frequently used to for audio classification and for speech recognition. And so with that research, I did some reading on the papers, and I figured, oh, I can take a crack at maybe I can consider using audio features instead of just raw sample data, right? And some of you, I can see, probably already know this. There's many kind of audio features, right? There's the amplitude modulation, there's auto correlation, the common, like one of the popular one, the MFCC, and the OBSI, all this stuff. So there's many of them, and we're using a particular feature, a particular tool called YAFI to do the feature extraction from the from our collected audio clips. Not to get too much detail in how the feature being calculated, because it sounds like a lot of you guys already know this. But one thing I want to share here is that there's so many features, and for each individual audio feature, as you can see here, each feature is actually calculated over by each frame, right? And by step size, which means that for the 1 second audio clips, because I have 8,000 sample size, I will have 16 frames, and each individual frame can generate quite a few data points, meaning just for one audio feature, you will generate a lot of data points, right? And every single data point itself will be a machine learning, training the training data's feature, right? So you end up with still a lot of a data point for each individual training examples. And then the big question we want to ask ourselves is that, so which one will work, right? Well, which one of this 29 audio feature extracted by YAFI is useful? And the answer is, I don't know, right? And for folks who are really into signal processing, maybe you all have a clue of a better clue on what feature is more predictive. From my perspective, I have no idea, right? I have no idea which one feature will work the best. But that will not stop me, right? It doesn't matter. So what we do here is that we just throw all the data points generated from all the audio features. We create a big training set with a total about, I think, for 29 audio features, and completely extracted. We have about 3,300 or so data points for 1 second audio clip. So what we do here is that we started by, again, we use the magic of just quick evaluation and numerous testing. We throw all the data into DataRobot. We just do a blind testing. So again, right, with any machine learning project, this is one of the approach you want to take, which is that don't think too much about whether your feature is really cool or not. You really want to get as soon as possible, have a round of testing and let machine to learn from that and tell you which direction you want to go deeper. So that's what we do. And I will yeah, after this slide I will probably bring up the DataRobot to give you an idea of how this will work. So basically we end up with okay, I lost that slide. So the point I'm trying to mention here is that you want to have quick testing to validate your hypothesis, to do effective research, quick research on the right features, and drill down to find out the most accurate and efficient model. And the one we eventually find out, okay, this is the slide I want to use. So basically, after we started testing with that 3,000 data point out of 29 auto features, we got a much better result. All of a sudden, our accuracy rate shoots through the roof. It's becoming 90% now, which I'm very happy about. But then extracting all these 29 features is extremely expensive. You can imagine if you do that in production, you have to extract all these 3,000 data points for 1 second. It is not practical, right? It's just too slow. So that triggered me that I really have to come down to see what I have a better way to do it without losing the accuracy rate. So I did a feature impact analysis with DataRobot. And the feature impact analysis tells me that, oh, there's actually 30 of the features, 30 of the data points are out of the 3,000 are very impactful. And these 30 is actually kind of spread out into more than one auto features. There's like a dozen of them. So I did, then I said, great, I just picked this 30 data point and do a training again, only with that 30 data point instead of 3,000. And again, I found a really accurate result. It's not as good as all of them, of course. The 3,000 is more predictive. but the 30 is only a few points down. And I'm pretty happy with that because this tells you can train very efficiently. But then I asked them, still not good because all the 30 data point is spread out into multiple audio features, which means you still have to extract all of them, and in production it will be not going to be very practical. So and then I did some further research. I found out of these 30 data point, it seems that more than half of them is actually coming from one category, which is OBSR audio features. For folks who don't know, OBSR stands for octave band signal intensity ratio. So observing that 15 of them is actually out of 30 are from this one group only, I got this idea of saying, why not just do a training with only data point from OBSR, which altogether have for 1 second audio clip with my 8,000 sampled data, you end up with about 112 data point, which is more than 30, but it's very efficient to only extract one audio feature for OBSR, right? And then the testing results are very pleasing. So with about 112 data point from OBSR, I end up coming with about almost the same accuracy as the 30 topmost. It's still a 1 or 2 point less than all the audio feature one, but this is decent enough, right? It's very practical. That's how and then we decided. So the practical approach to this project is to use OBSR as our features and using about 112 data point. So I will take a pause here. Any question on the feature engineering?
I assume the feature labeling was mostly focused toward human voice, and there were also some assumptions being made when generating the training samples and creating training samples. Would those assumptions have any impact on the choice you made in terms of the audio features or the sampling rate or anything else? For example, if you had more music-oriented data that is causing feedback, then you might have different pattern in terms of how the frequency distribution is. Could you comment on that?
Yeah, definitely. That's a good comment, actually. And this is similar to the kind of a concern folks raised early on, right? Which is that with artificial generated data, with the limited setting we have, whatever accurate result from this training, this data set may not be completely, representative of the real life scenario. I totally agree. There's no doubt on that. So the answer for that is that. So I mean, here's what I learned from this project, right? The representation project is that I think we successfully validated the hypothesis, which is the initial hypothesis is that if a human ear can see it, it's probably okay with machine learning and do something about it, and also detect it with fairly accurately, right? That's a hypothesis, and I believe with this, well, I totally agree that it's not being able to maybe detecting the whole life, real life cases, but the hypothesis is still validated, which means is that the next step, if we do see this valuable, we should just collect as much as possible production data and train it again to make the model more robust. That's how I respond to your question, right? That's how I see it. Does this answer your questions? Oh, and also just for the interest, right? That you mentioned music. It's actually very interesting testing. So after we do this, we actually tested with a lot of high, all kind of music, like the rock and roll, the high pitched one, the heavy metal one. Surprisingly, it's very accurate. Those are all labeled as normal without being mislabeled, detected as feedback sound or whatever. Yeah, and I thought some of this music with a very strong rhythm can be possibly misclassified as an echo. It's not true. It's actually correctly identified as normal, which is pretty good, pretty cool result.
Peter, we have 12 minutes remaining.
Okay, let's keep going.
We can chat.
Yeah, we may not have enough time for Q&A, but I think we did we spent a decent time on Q&A already. So let's keep going. So one thing I want to mention here is that I keep talking about using data robot for quick iteration, right? And that is actually one of the very important many machine learning projects, and one of the key message we want to deliver, for this representation. But then at the end, you really don't. You need to get a model exported, for either in a service or in a client, in a device. It has to be useful. And a DataRobot is not quite supporting that model, and they don't quite support the exporting of your model, because they really want to force you to use their prediction service, which we probably don't want to. But that doesn't stop us, right? The thing is that in any machine learning project, writing the algorithm and implementing it is really the small task, right? It's probably only 1% of the time. For most of the project, it's not about a machine learning project, not writing code, right? It's about finding the be creative on the feature and do the training and nail down, to figure out what is a model, right? So what I'm trying to say here is that, so with DataRobot, you're able to get most of that done. So once you know which model works the best, like DataRobot will actually train 20 different algorithms, from forest tree to gradient boost tree to all kind of thing. But eventually they will tell you with the leaderboard, tell you which model works the best, what feature set, right? So once you got that, then it's an easy task. Once we got that, we started writing, with Python Jupyter Notebook to implement the model using some popular package such as scikit-learn, right? That's one of the popular Python machine learning library. So I will show you the notebook later. It's only like 20 lines of code to actually implement that. So that's why I say this is really a small deal, and you don't really care. And the beauty here is that when you're coding that, you can actually copy all the hyper parameter that you got from the DataRobot training, and you just put that parameter into your code. And we just did that, and we found it. We trained with our own code is similar result with DataRobot. So yeah, just want to share that out as well. So this is actually concluded our presentation, and let me switch to the DataRobot one. Oh, I lost that, so I have to log in again. We probably don't have too much time to demo this. I just give you a quick feel on how this works. Okay, so we are logged in, and I think this is the project I was looking at last time. Yeah, so this is the project I want to show. So this is basically I created. This is a project with all the Yafi features. So I throw in about, you can see from the text here, which I'm putting my mouse cursor over. So you can see there's about 3,361 data points. That is basically the total number of the data point extracted out of the 29 auto features I mentioned earlier. And in this DataRobot, I only have a 12,000 training example. I don't have that all at 45, because with DataRobot, the license we have with them is actually only supporting us not a large enough data set. But even with 12,000 data set, I got a pretty accurate training. But with our own coding, when we do the Juniper coding, we actually be able to train with a much larger data set, which is even more robust model I would consider. So once you throw all your, you create this large CSV with this 3,000 column in there, you can do all kind of experimentation very quickly with DataRobot. You can actually, just train automatically with all of them. By default, you can actually say do automatic training, and DataRobot will analyze your CSV and recommend up to 20 or 30 different models to train in parallel. This is actually what I do initially. So I basically just throw this. I train with all these 3,000 features with about 30 models, and second day I look at my model. I got a leaderboard, which is here. So, well, I already deleted a lot of models, but so there's not that many left anymore. But basically, when you do initial automatic testing, you will end up with a lot of model, not just gradient boost tree, but the forest tree. There will be just the simple logistic regression. There's some kind of TensorFlow classifier in there. So you actually end up with a lot of model training in parallel, and you can see from your from a few dash chart here, for example, from speed versus accuracy. This will allow you to make a better assessment on the accuracy versus speed, right? As I mentioned earlier on, you want to be practical. So, for example, in this case, one of the model here is very accurate, versus this one is slightly more accurate, but this is the model on the left saying that they take less time to score, right? So this is actually the most efficient one. So this will give you some hint that which model is more appropriate from practical point of view, right? And so there's all kind of tool like this. You can also do so when you select a model, you can do feature impact analysis. So you can do and this will tell you which feature is actually very predictive of your target state. So there's all kind of basically I consider developer debugging tool. And not exactly debugging, but similar idea. You got an analytical tool to help you to make decisions on how to handpick features and how they perform in the detection process. So I think that's all I have for DataRobot, given the time we have. Any questions so far?
Do all developers have access to this?
No, you don't have access by default because we have a limited license for DataRobot. I would say if you're interested and if you have a machine learning project and you want to do you want to use it, then send an email to Andrew Greenhut for access.
Okay, thanks.
I have one question, Peter. So if what is the latency right now? If you have a audio clip, how much time it takes for you to know whether it has feedback or not?
Let me show you I got your question right. So you're talking about the latency of the actual prediction?
Yes, overall. So you are given a clip, right?
Yeah.
Let's say a second clip. How much time overall it takes to get to the outcome? Yes, it has a feedback or not.
Okay, sure. I can. So there's a few numbers I want to give you. First of all, from prediction, just the prediction API itself is take about for DataRobot it's very fast, but in our coding we found it's not as quick as it is. But when we do the hackathon project, we integrate our model with the audio engine team, right? With from Costal, and the roughly is about 100 milliseconds for. Actually less than that. It's roughly about 70 to 80 milliseconds for each prediction. That's what we get back then. It's a C++ implementation of the model. And then there's other time, right? So when you actually do the user experience right, the way we did it with Hackathon is that the audio engine team will, for every single 1 second of audio clip, audio just pass, they will send us the 1 second verse, and they keep they're moving the window by half a second. So every half a second, they move the previous 1 second one to prediction to the model to do a prediction. So you can see that the responsive, from user point of view, they will every half a second they will get an answer whether there's a feedback present or not.
Okay. So are you planning that in future you guys may be building some kind of API interface where you can provide the data, the audio stream, and based on that it will keep providing the result whether it has a feedback or not, so that application can do something, so that if information can be ballooned to the user as well, so that if we can't fix it, a user may be able to at least know that okay, I need to do something.
Yeah, we do plan to do that, and the current state of the project is like this. So we have a C++ implementation of the model. We train with C++, and we have a C++ object in a C++ format, and exportable to a C++ runtime, right? As demonstrated that we actually successfully integrated, embedded, right, not as a web service, embedded into audio engine. So the Patrick's team actually did some work on this, and basically the way we did is that we usually two new events, right? It's called feedback present and echo present. So when when we detect feedback, when audio engine detected the feedback and echo, they will send these two events to go to a client such as GoToMeeting. So that's how we did it in Hackathon time. And we also have a Python model for this. So we could actually create a web service for it for those applications who can afford to do the in a web service manner. So there's many ways to deploy this.
Okay, thanks.
Yeah. Any other questions? Okay, if not, we are right on the time. So 11 o'clock now. I will give you one quick thing, just for folks who actually want to play with this. So we have a very detailed wiki page describing this project, because as I mentioned earlier on, right, this is a reference implementation, and we want folks to be able to come here and without talking to me, they should be able to self onboarding, and the project is actually on Bitbucket, and the location of the project and the data set for this is all documented in this wiki page. So I already received quite a few email since the last time Wintower sent the email out. There seems to be quite a few folks are really being able to just onboard themselves and play this project completely on their own. So I would encourage you guys to do that, to learn machine learning, and also to we can have constructive discussion to see whether we can improve this better in the future for practical purpose. So just wanted to let you guys know that, and the README file on the on the project will give you a very detailed instruction on how to retrieve how to get all your dependency for the project. So that's all I have for today. I want to say thank you for your time to joining us. And if you have any feedback or questions, please feel free to send to me.
All right. Thank you for joining, folks. Hopefully this talk can be helpful to your own machine learning project. If you do need a sounding board or some advice on your own machine learning project, please feel free to reach out to Peter or myself, or you can find us on the machine learning channel on Slack, and we'll try to be as helpful as possible. And also, in the end, one more commercial time. If you have any talk to present for the overall company, overall engineering community, please go to the BDI Tech Talk Wiki and add your name there, or reach out to Raja Gopal, who is our chief architect. And we look forward to hearing more from you. All right. With that, thank you, guys. Have a good day.
All right. Bye.